Uh, okay, is it working now? Hang on. Let me check the audio's fine. Okay, I've finally got the visuals working. Is the audio fine? Let me check. Okay, I think we're good. I think we're good. Oh, I don't know what happened there. Yeah, so obviously there's like if on Twitch anyway, that first 3 minutes would not be on YouTube or anything. That was just I don't know what happened there. I do not know what happened there. But I think we're up and running now, hopefully. Obviously, do let me know if it messes up again. But hopefully, you can see and hear what's going on now. Do-do-do-do. Okay, let me check the chat. Get that up and running. God, what a palaver today is. Okay, it should be good. Hopefully, I can see it on my one, so hopefully it should be fine. Okay, yeah, apologies as well. I wanted to be on a bit earlier, because I did want to do some more stuff today with maths, but some came so I have to be a bit late. So I think really what the plan is for today, I'm only gonna be on for like an hour and a half. Pretty much just finish the rest of this paper. Uh, I guess if you have any time, I can go over something else. I don't know. I don't want to then start a new paper because I don't think I have much time. So I think the plan today is I think that I checked. There's 4 more questions, but there are meaty questions of this paper. So I think I'll just go through the rest of the paper. So, but before we do that, actually, I do want to address what's it called? Uh, this circle question that I said yesterday I wanted to explain again. Uh, and essentially what it was is we had to find the equation, the equation of the circle, and then find the centre and the radius. And then once we found the circle, right, we wanted to find the furthest point away from the origin, which would be about here, right? It was a bit wishy-washy yesterday, and I think the best way I can explain is due to the fact that really the furthest points on the circle have to be on the radius, therefore have to pass through the center. So let me just illustrate this a bit more. So obviously that's our circle, roughly, and P is about here, right? The furthest point on the circle away from the origin. And really, it has to pass through the center because it has to lie on the radius or the diameter, right? So obviously this diameter here is the furthest away. And the reason that is due to the fact that really, for any circle, right, with a center, if you draw from one point of circumference to the other, you have chords, right? Now, actually, notice that the further away we are from the center, so this chord here, well, that's going to have smaller length than when we get closer to draw lines or chords towards the center, right? Hang on, let me draw that again. So obviously, say the center is here, really rough circle. So if we draw a chord, I don't know, there, for instance. But then notice as we draw chords towards the center, it's going to get larger in length, right? And then eventually we get to the diameter. So it passes through the circle. And this chord, particular chord, the diameter, that is the longest length you can draw in a circle to hit 2 points of the circumference. So the diameter is basically the largest length in the circle. And so why that is relevant here is because, again, to get to the furthest point in the circle, from O, we have to make sure it passes through the center. So that means you go from, this is really bad drawing here, but essentially without all of that, I guess the circle looks a bit like this, doesn't it? There we go, that's much nicer than yesterday. So O, and then obviously our center was here, and then P would be about here, right? The furthest point from O. And really, it has to line this line essentially, this diameter, right? Obviously, it's a bit bendy, but obviously with a ruler, uh, the longest distance away, the line distance has to be on the diameter, right? Because like I said here with this example here, if you then don't include the center, you have a chord which is a smaller distance than the diameter. The diameter, like I said, is the biggest chord you can draw in in a circle. So therefore, to get the furthest distance by that point, it has to pass through O. And that, oh, sorry, it has to pass through the center. Well, it has to be on the diameter, so it has to pass through the center. So that means the distance has to go from O to C, our center, and then the distance from C to P. And C to P will just be the radius, right, which was 13 or something like that. And then OC, we computed the distance by Pythagoras is root 89, and that would be your biggest distance. Okay, that was what I wanted to say yesterday, but I just came up with a bunch of mumbo jumbo. Okay, so I just wanted to clarify on that first. Hopefully that makes sense. Hopefully. Uh, but now we're going to get on with the rest of the paper. So, yeah, so we finished on this integration by parts question, and now we're on this one. So we're looking at sequences and series, and actually, the first part is a proof, actually, and it says in an arithmetic series, the first term is A and the common difference is D, so it's a generic arithmetic series. I'm going to show this formula here, which you should be familiar with. The sum of the first n terms of the series, right? Okay, so this proof is actually in the textbook or whatever. I believe you are meant to learn the formula. See, I think you need to know the sum of the arithmetic. So that's obviously n over 2, 2a plus n minus 1d. And you also need to know the geometric summation, which was, well, that's in the formula book, but I think it's a lots of r to the n minus 1 over r minus 1, something like that. I'd have to check the formula, but I think that's it. You need to know how to derive both of them, which are both should be in the formula book. But I'll go over it now, essentially. Um, And okay, let's get rid of this. So obviously that's our aim, right, to show this formula here. But where we're going to start from, wow, not much we can start from. So let's work with what we do have. So we're given a generic arithmetic series. So what is an arithmetic series? Well, you add in all the terms in the arithmetic sequence, okay? So obviously sequence, you just list the terms. A series is adding the terms. So let's start the sequence and then we can see what we add in. So also the sequence, well, the first term is A, then we add a common difference, A plus D, then you add the same one, A plus D, 2D, A plus 3D, A plus 4D, and then it goes on and on and on. And then actually the final term is going to be A plus N minus 1D, because then that gives us N terms, right? That's the nth term, and it has to go up to N terms, right? You can see this because this is basically equivalent to A plus 0D. Obviously, A as its own. So if you start from 0 and we have to get to N, we have to end at N minus 1. So then you have N lots of D's, so that means there's N terms. So that is the final term here, not A plus ND. Not that, okay. And that is actually the generic form of an arithmetic sequence, what we should be familiar with. A plus n minus 1d. That's you should hopefully recognise that. But anyway, there's n terms here, which is good. So that's our sequence, right? So then our series is going to be adding them. So Sn is going to be a plus a plus d plus a plus 2d, and then it goes on, and then you have a plus n minus 1d. Cool. Okay, well, I do know that there is a trick you need to know of this, and actually, you can also rewrite this as saying Sn in reverse. So that's going to be a plus n minus 1d plus dot 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 plus a plus 2d uh, yes plus a plus d plus a. And actually the trick is to notice these are the same, so we can add them two together to get 2Sn. And why is that? Why are we doing two lots of Sn? Because actually notice this here. We have n over 2, so if you times by 2, you get 2Sn is simply n lots of. So I think it's a lot easier to see what happens when you have two lots of Sn. And then see where we go from there. So 2Sn. So actually, I think I should write more terms with this actually to be a bit more clearer. Uh, yeah, I'm gonna do okay. This is what I'm gonna do. A plus 2d, and then I'm gonna say add dot dot dot, and then I'm gonna say a plus n minus 2d to the term before this one. And then you add in the last term, and then I'm gonna do the same here, and you're gonna see why in a minute. So you're going to have a plus n minus 1d plus a plus n minus 2d, and then plus dot dot dot, and then plus a plus 2d plus a plus d plus a. Okay, so then we have 2Sn, and the idea is essentially we can create pairs between these two. So let's have a look. And actually, notice it has to look like this, n minus 1d. So that's going to guide us. So say this is 2Sn, that's going to be n lots of 2a plus n minus 1d. Okay, so 2a, it doesn't look too nasty, but this bit looks a bit nasty, right? So I think we're going to have to look for ways of getting n minus 1d. Actually, I'll leave that there. I don't know why I'm cancelling that out. 2a plus n minus 1d. Well, let's have a look. Well, actually, notice if we then link the first terms together now of the two series, that's going to be a plus a plus n minus 1d. And notice why, so I'm adding a to a plus n minus 1d. Then, I guess actually cross this out. I can pair this together, right, with this weird shoe shape, and I'm going to do the same to the next term, right? And then I'm going to say, wow, this is going to be a plus d plus a plus n minus 2d. Plus, and then I'm going to do the same to the, and then we're going to do the same to the next one. So the next one would be a plus 2d, but then in the next term in the second sequence, a plus 2d. If we follow this trend here, we're doing n minus 1 each time, aren't we? Uh, So we're going to a plus 2d plus a plus n minus 3d. Okay, and that will continue, and then we can do the bit here. So do the final two terms together. Oh, actually no. No, so these are the final two terms, aren't they? Here. Okay, I'm not. Oh God, this is rubbish. Okay, I'm going to get rid of this bit here. So what I'm going to do is make sure that the terms have the same amount. Okay. On each the same terms, right? So I can easily collect them together. So that's just going to be a plus d and then plus a. So I'm waffling a bit there. But what I'm saying is now I can now pair because these are the final two terms on each series. We can now pair them together because they're in the same position, right? So this is what I'm doing. Okay, so I'm saying this is the first term. We go on the left hand side. This is the first term, and then this is the first term of the second series. I'm pairing all the first terms together and adding them. Then I'm pairing all the second terms together and adding them, and then I'm doing it the third term, and then I'm doing it the final two and the final term. I'm pairing the terms in the series together and adding them, and then that's going to be dot dot dot, and then we're going to be adding the second to last term. That's going to be a plus n minus 2 d plus a plus d, and then this final term here is going to be I don't want to do that. Let's do it off the page, I guess. And then the final term is going to be a plus n minus 1 d plus a. Okay, and actually, what do I notice about this series? Well, let's do some simplification, right? So that's going to be a plus a. We can simplify to 2a plus n minus 1d. Then the second bracket here, well, a plus d, that's a d, and then plus a, that's going to be 2a again, plus d plus n minus 2d, so that's n, so that's going to be nd minus 2d plus d. That's going to be just nd minus 1d, so nd minus d, which you can factorize to say n minus 1d. And then the third term again here, that's going to be a plus 2d plus a, so the 2a again. Plus, and hopefully you can see what's going on here. 2d plus n minus 3d, that will go to n minus 1d. Because we have minus 3d, add a 2d, that's minus d. And that continues. And then our second to last series is a plus n minus 2d plus a, so that's 2a. And then n minus 2d add a d, so minus 2d add d minus d, so n minus 1d. And then the final term, well, very simply, a 2a plus n minus 1d. Now, what you should easily recognise here at this point is actually these are all the same terms. So we can say this is 2a plus n minus 1d. Cool. And actually, isn't that the formula essentially with just a coefficient of n over 2? Um, but this bulk of it is the same, right? And actually, 2n or 2Sn, which we've got here, is n lots of what we've got. So really, we just need to times by n. So we need to, but there's going to be a factor here, isn't it, of a k. So there's k lots of this. That's 2Sn. Okay. But actually, how many pairs are there? Well, for each term by term, we're creating a pair between the two series, right? So we're using two terms per pair. But but there are n terms in each series, right? So we are creating for each term in the sequence, we create a pair. So there's one pair here, two pairs here, three pairs here, n minus 1 pairs and n pairs. So actually, in total, there's just going to be n pairs because really because obviously n terms in the in the series, right? In the n terms in the sequence, but we've created for each term we've gone in the sequence, we've created a pair. So n pairs. So there's going to be n lots of this, right? So each pair has its value, but there are n pairs, so we just times by n. Okay, hopefully that bit's clear. I guess to kind of reiterate, I guess to drive home the point. So all what we've done here is we added the same series again to get two lots of it, but we rearranged the series to go from the first term to the last, to then the last term to the first. But both of these series will still have n terms in each of them. And what we've done is then matched the first terms of both of them and paired them together and added them. And then these each pair gives us the same sum here. But then as there are n terms, that means there are going to be n pairs, okay? Because each term is getting paired off. So they're n terms are n pairs. So each pair adds to this, and there are n lots of them. We get this result here. And so that's two lots of Sn, because remember this is Sn add Sn. Because if we create a pair, that means we essentially add in the series by itself. So we get two. And therefore, Sn is just n over 2 of 2a plus n minus 1d. And that is your proof there. Okay. Oh, okay. That is, I think that's a proof in the textbook, but it's just something you have to be aware of. Okay. Oh, hi, yeah. Okay, let's have a look at this next part of the question. So it says, James, oh, let me get rid of some of this, actually, make it clearer to see. Okay, so we are told James saves money over a number of weeks to buy a printer that costs 64. He saves 10 in week 1, 920 week 2, not for 840 week 3, and so on. And it forms an arithmetic sequence. So probably we could see here that the first term is going to be A of 10 and D is going to be minus 0.8. Because we're minusing 80 pence, right? And so I think we can do something with that. And it says it takes n weeks to save exactly 64. So if he's saving every week, then we need to take the overall summation to find how much he saves over n weeks, okay? So again, let's just copy down info. A here is going to be 10 and D is going to be minus 0.8. That means the sum of the first n terms that gave us n weeks. Well, we just use this formula, right? So it's going to be n over 2 of 2 times 10, it's 20, plus n minus 1 of minus 0.8. And we can simplify this bracket, can't we? So it's going to be n over 2 of, well, 20 minus, and this is times it by 0.8, by the way, minus 0.8n plus 0.8. That will go to n over 2 of, well, 20 minus 0.8 is going to, plus 0 is going to be 20.8 minus 0.8n. And I'll leave it there for now. So what's it said? So then it shows that it takes n weeks to save exactly. So we're going to need to equate this to 64, right? Because it's telling us the summation will go to 64 here, and we have to get a quadratic. Okay, so hopefully we get a quadratic that matches that. So that has to equal 64. So we have to put that to 64. Okay. Well, first of all, let's get rid of this 2. You don't have, you can times it out as it is, but let's just make it nicer. So this would be n lots of 20.8 minus 0.8n. That's going to be equal to 128. And then we can expand it out. So we can say 20.8n minus 0.8n squared. And I'm going to minus 128 to make it look like a quadratic. Therefore, if I just get rid of the minus, I get 0.8n squared minus 20 0.8n plus 128, that equals 0. So I'm just dividing by -1 there, just to get rid of the negative on the n squared here. Okay, but we may need to make it look like as this quadratic here. So n squared, but I have 0.8 n squared. So to get it to 1, I'm just going to divide the whole thing by 0.8. And hopefully that should match that at the end, if we've done it right. So then I'm saying divide by 0.8, both sides. You don't have to write this, but I'm just saying what I'm doing. So that should be n squared, and then minus 20.8 divided by 0.8. That's going to get 26. So that's minus 26n. Then 128 divided by 0.8, you get 160. And hopefully that should be the quadratic they got right. Let's have a final check. Yes, it is. Cool. That's great. Then it's to solve the equation for 1 mark. So really, you can just bung it to the calculator really, and just state the values. So roots are, wow, put that into the calculator. Where you get n is 16 and n is 10. Okay, so what's it saying now? I think I know what it's going to say now. I can kind of guess, but let's see it. Hence state the number of weeks it takes to buy the printer, given a brief reason for your answer. So we need to find the value of n, essentially. That will give us the result, right? It's the kind of like exponentials, right? You have to reject certain solutions to give you like a negative value that you can't have. So it's the same sort of thing here. We have two solutions, but we need to pick one. So which one we're going to pick? Now, actually, if you practice enough past paper questions, it should be quite easy to see that actually it should be the first solution. So we take n is 10. I'm going to explain why. Look, consider this graph, right? So the roots are 16 and 10. So 10 is going to be like here, and 16 is going to be like there. This is our graph, right? N squared minus 26n plus 160. So it's going to look something like this, I believe. Now this represents this n squared here. This represents Sn. So actually, it has to be positive, right? It has to be above the y-axis, and it is above the y-axis before 10. So that's great. But obviously, then it goes negative after 10. So that means after 10, it doesn't make sense, right? Sn has to be positive or zero, right? Because we're saving money here, because it's money, we can't have negative money. So actually, once it reaches zero, after that, it doesn't make sense. So if you consider just the graph of the sum, which is a quadratic, right? You can't have negative amounts. So anything if when it dips below the obviously the x-axis, the y-axis, you get an invalid solution. So for that reason, it has to be the first one before it hits underneath the y-axis when y is 0. Alternatively, when you have cases of multiple solutions and you're not sure which to pick, try and substitute it into the I guess into I don't know, the equations you got given. And well, obviously, if you plug n in equals 16, you're going to get the series to be 0. That's not really helpful. But what if we have un? Remember, un is a plus n minus 1d. Well, a was 20, right? And then d was minus 0.8. What if when we substitute 16? What would happen then? I think you get negative value, but let me check. What should give a positive one? Yeah, it gets a positive. Okay. Okay, that gets a positive, so we can't do anything there. But essentially, so the Sn is negative, right? Because if you consider the graph, uh, so you cannot have uh n greater than 10 because when it goes greater than 10, um, it fails, right? The series breaks down. Well, in order for the summation to be less than zero, the terms after 10 will have to be negative as well, I'd imagine. But that is essentially the reason. So take n equals 10 because I guess after n equals 10, so n greater than 10, the the series Sn becomes negative, uh, which cannot happen because obviously we're saving money. You cannot then get negative money. It doesn't make sense. It cannot occur as you cannot have negative money, I guess. Okay, I was kind of hoping the UN would be negative there, but it doesn't matter. There are other ways we can check the feasibility of the solution. But that's essentially the sort of reason behind that. They do occasionally like asking you stuff like that. With series to work out which solution you need to accept. It's not immediately obvious, but if you practice, you realise the first route usually will be the one you take because after that the series becomes negative, and usually the series cannot be negative in the context of money or whatever. Uh, yeah. So again, also the mark scheme for the reasoning they say he has saved up the amount by 10 weeks. Yeah, so 10 as well. He would because obviously this occurs when he saves 64, but then the first time it reaches 10 weeks, it's going to save 64. So then anything after that, well, really, he can't really save any. He's saving more, or somehow less, but I don't know. But he's not going to save 64 after that, isn't he? The first time you reach 64, that would be the sensible solution. You would choose the smaller number again. The reason is because the smaller root is because it's positive before it. Anything after the first root will be going negative, and you cannot have negative series. And then it says he starts saving negative amounts of money in week 14. So that's where UN, I guess, or whatever turns negative. So 16 doesn't make sense. Okay, so those are the reasonings they give, but that's essentially what you need to be looking for there. Okay, cool. Uh, okay, now we have a trig question. Doesn't look too nasty actually. So part A, we're given this equation. We need to show that we can get to this. Pretty standard. But the first thing I notice is we have an addition in the in the angles x minus 60 and x minus 30, and we need just x on its own. So I think we're going to need to use the addition, which is in the formula book of sine a plus, well, sine a minus b, I guess, and that's going to be, I believe, sine A cos B minus cos A sine B, and cos of A minus, well, it's going to be A plus B, isn't it? No, A minus B, sorry. Uh, and that's going to be cos A cos B plus sine A sine B. And that's in the formula book just to show. Hopefully I copied it down right. You don't have to remember that bit. Um, well, it's here, right? Sine A plus or minus B. Obviously, you want minus B because we're subtracting. That's sine A cos B minus cos A sine B. Cool. cos A minus B, and then it's a plus. So when you have plus or minus, and then this weird minus plus, that's telling you if you take the sign on top is the order, right? So if you take positive, then you have to take the negative on top. If you take the minus on the bottom, so say we're saying cos of x minus 60, for example, then you have to take for here the positive because that's on the bottom. But yeah, apart from that, it's in the formula book. So cool. So really, then we just use this. So therefore, we can say sine of x minus 60. Well, that's going to be sine x cos 60 minus cos x sine 60. Now, actually, cos and sine 60 evaluate to actual numbers, doesn't it? So cos 60, I'm in degrees here, so cos 60, that's going to be half. That's going to be half x. What's going on here? Half x, and then minus, I believe that's root 3 over 2, but let me check that. And then sine 60 would be root 3 over 2, yeah. Minus root 3 over 2 of sine x here. Let me write that a bit clearer. Sine x minus root 3 over 2 cos x. So I'm just evaluating the cos 60 and the sine 60 because they're actual numbers, right? Likewise, we can do cos x minus 30 degrees, and that's going to be using the addition formula. That's going to be cos x cos 30 plus sine x sine 30. That's going to go to our cos 30 is again root 3 over 2 cos x. And then sine 30 will go to a half sine x. Cool. So we've got expressions for this in terms of just sine x now, in terms of just x on its own. So I think we're in a good position now to simplify this. So sub this in. So therefore 2 sine x minus 60. So 2 sine x minus 60 here. We're going to just double this result here, right? So 2 times a half, that's just, well, that's just going to be sine x minus root 3 cos x. If you just double it, and that's going to be equal to just cos x minus 60, so substitute this in. Root 3 over 2 cos x plus a half sine x. Okay. And I think we should group the sine and x's together. So therefore, sine x minus a half x is going to be a half sine x. And that's going to be equal to root 3 plus root 3 over 2 cos x. Which is 3 root 3 over 2 cos x. That's when you just group the sine and x and coses together, right? Now I think I can times by 2 to make it a bit nicer for me. So therefore, sine x is 3 root 3 cos x. Now let's look at the answer we have, what we need to get to. Tan x is 3 root 3. Well, actually, we have a 3 root 3 here, so we're quite close. But how do we get tan x and get rid of all the sine and coses? Well, actually, you should know this identity here. Tan x is sine x over cos. So I think if we then divide by cos, we therefore get tan x is 3 root 3 cos x over cos x goes to 1. And so I think you're just simply left with tan x is 3 root 3, which they want. Cool. Then it says to solve this. So this is quite usual. They want you to use the identity proof from part A to then solve part B to make it easier. Well, look, this is in the same sort of form as this, but we need to make it match exactly. There's something going on with the angles here. Well, I noticed that sine 2 feet. Well, this is probably going to compare, right? I think we have to say 2 theta to match the sine angle. That's going to have to equal x minus 60, because then we're going to need to substitute x in here for tan. So if 2 theta is x minus 60, well then x, which we're going to substitute for theta, that x is going to be 2 theta plus 60 degrees, right? And therefore that would mean 2 theta would replace, well, this should be the x in the x version. But let's check this holds for cos, right? So 2 theta plus 30. Well, if x is 2 theta plus 60, well then substitute x into here, you're going to get 2 theta plus 60 minus 30. You're going to get plus 30. 2 theta plus 30, that's great. So the angles match up here. Yeah, so if you ever a bit tricky, oh, it looks similar, but I can't exactly get down to what angle should be used and what substitution. Just make a substitution, right? Try and make explicitly clear what you need to compare with. So here I'll notice the angle sine of 2 theta has to be the same angle here. So 2 theta is x minus 60. And therefore x then is this, and then I can compare it with cos. And actually it turns out they're the same angles as well. What that means as a result is, if these two are the same angles as these, that means we can substitute tan x and x here. So that means tan of 2 theta plus 60 is equal to 3 root 3. So I'm going to write that down here, and then we can solve that, can't we? So tan of 2 theta plus 60 is 3 root 3. Okay, and then we just solve this, right? So then if I say arctan, so 2 theta plus 60 is tan to the minus 1 of 3 root 3. That will be, has to be in degrees, right? Yeah. You get this decimal, right? You get 79.1066, blah, 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 blah. Okay, so that's what we call our principal solution. So there are going to be more solutions depending on the graph, right? So our tan graph is going to look like this. Obviously, you should remember that with an asymptote there, and it'll continue on. So when it's 79, it's going to be about there, isn't it? It's when tan x is 3 root 3. Now, actually, if you continue on the graph, it's going to have another solution there if you continue at another 180. Likewise, it can go backwards by 180 if you then consider the graph. So there are many solutions. So therefore, we need to consider, well, what interval, what values of x do we need, or theta do we need to consider? And that's where we then look at the domain. Oh yeah, you okay? Well, actually, we're given this, aren't we? 0 has to be between theta and 180. So I'm going to note that down. Was it less than or equal to 180? I don't think it really matters, really. Okay, but that's for theta. Notice here we're solving for 2 theta plus 60. So what do we need to do? We need to adjust the range. So I'm going to then times by 2. So times both parts by 2. So 0 times 2 is 0, obviously. And then 180 will go to 360. Then we're going to add 60 to both sides. So 60 has to be between 2 theta and 420. And now, 2 theta plus 60. Has to be between 420, right? So that's our range when you adjust for the actual angle we have. Okay. So that means we need to look for all the solutions between 60 and 420 for this angle here. Like 79 lies in it. But if we go back and look at every solution, it's going to be 180 degrees from each other, because the graph tan, oh God, what's going on here? The tan graph repeats every 180. So that means we add its solution to get the next solution, or backwards, we add or minus by 180. But if we minus 180 to 79, that would get a negative solution that will fall outside our range. So then we can really only go forwards. So that's going to be 79, and then we're going to do 79 of this, add 180 to then get the next solution. So then that's going to be 259. 0.1066, blah, 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 blah. And then let's check 100, add another 180. You get 349. So that'd be the next solution. But actually, 349 is over 420. That'll be outside the range. So actually, that means these are only two solutions we can have here. So I'm going to reiterate then. In this interval we have here, 2 theta plus 6 theta plus 60 has to equal 79.1066, blah, 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 or 259.1066. Okay. Okay. Well, that's solving for the angle 2 theta plus 60. We need to solve for theta. So essentially, we need to rearrange this for just theta. Well, I think if you then subtract 60 by both sides, you can have, that would be 19.1066, wouldn't it, if you subtract 60 to both sides? And that would be 199.1066. Cool. But that's then 2 theta. We need theta. So then that means theta is divided, we divide by 2 to everything, right? So 19.1066, whatever, divide that by 2, you're going to get 9.553, and so on. And then this 199 will be divided by 2, that'd be 99.553. And actually, that's a theta, so that's our solution. Now, that's in decimals. Does it specify to one decimal place? Okay. So notice here it said solve for theta, not for 2 theta plus theta plus 60. Okay. We need to solve for theta. So make sure you check your angle there. Okay. So therefore, theta then to one decimal place is 5.6 and 99.6 to 1 dp. And hopefully that should be the answer. Let me check. Hopefully I haven't muddled anything up. 9.6 and 99.6. Cool. Okay, hopefully that made some sort of sense. But it's a fairly standard trig question. But obviously, the what angle and substitute, how you compare, it may be a bit tricky. But other than that, it should be fairly straightforward if you practice. But like I said, if you're a bit unsure about how to compare, make a substitution so it's explicit what you need to do. So here, again, I let 2 theta be the angle, and then literally compared. But then I noticed tan of x, so I need to substitute x in, and then I get this result here. So therefore, tan of 2 theta plus 63 root 3, and then I solve from there. Okay, paying attention to also adjust your range of values, right? So theta to 2 theta plus 60. Cool. Okay. Okay, we only got 2 more questions left. Okay, we got this one now. So we have a company makes toys. So this is a toy. Now I'm not going to go over the information because actually I think they've listed everything for us here. So face ABC, which is this little triangle bit here. That's obviously going to be a sector of a circle because obviously we've got an angle here and a radii. BAC, the angles 0.8 radians. Faces ABC, okay, the congruents are the same. So the bottom triangle bit is the same as well. It's saying, well, it's not a triangle. Sorry, it's a sector. And then that's a height. And yeah, basically the information is there. Okay, we give it volume, and we need to find the surface area. Okay. So, how would we find the surface area? Sorry about that. Okay, so surface area. So that is well, hopefully you can recall that's essentially going to be the area of all the faces, the area of all the parts that will be exposed on the shape. Now, I notice that this rectangle is going to be one of them, this ACDF. But also notice it's the rectangle on the other side, ADBE. That's also a rectangle, right? And it's going to have a width of R, radius R, and a height of H, right? So the surface area for that bit is going to be two lots of that triangle bit, right? So if I draw it, it's going to be R and H. Okay, so that's the front rectangle and the back. I also notice then the front sector bit, and obviously it's the same at the bottom. On the bottom, it would be the sector bit as well. So that's going to be two lots of that. So that's be 0.8 rads of this weird circle bit, this sector here, and then this little curved bit here. Now this is not going to be R because it's curved, right? This is corresponding to the arc. So we do not know this length, but we still know the height's going to be H. So this arc here, if I draw it, between H and this arc length, okay, and that is our surface area, right? If we break it down face by face, you have the rectangle part here, and there's obviously the front and the back of it, here and here. Then we also have on the top the sector bit of the circle, which is here, and then the back behind it on the down part of it at the bottom, that has the same face, and then we have this little curved little bit of rectangular bit on the side. Those are the surface area, right? If we add all the areas together. Okay. Well, actually, we know how to compute the rectangle bit. That's quite easy. That's going to be two lots of RH. And then for the area, well, it's a sector. So it's going to be, if you remember the area of a sector, so that's going to be R and R, by the way, for the radius. The sector, well, that's going to be two lots of half r squared theta, right? You should know the area of a sector is given by half r squared theta. Obviously, theta is the angle in the sector and r is the radius. So if we have r squared theta, but actually we know theta, don't we? It's 0.8. So this is going to be times by 0.8. And then we need to deal with this arc length bit here. Okay. But actually, if you think about it, this bit here, the surface area is just going to be arc length times h, right? Because it's kind of the same. It has the same sort of width, right? If you think about it, if we then shift this width up by h, you get the same at the end, right? So it's kind of like prisms, right? Where you have the cross section, and then you just times by the obviously you got the cross section, then you just times by the length. It's not too dissimilar in the sense that we have uh we have this arc length as the width, but then it's been has a height, has the same shape, but we're just elevating up by a height h. So really, we times the arc length, the L, this bottom line here, the curve, and then we times by h, we get the whole area of the shape there. Hopefully, you can realise that. So then, really, our mission is to just find the arc length. But actually, do we not know the arc length as well? Because we know the area, but you should know the arc length is also r theta. Well, that is going to be 0.8 r. Therefore, our surface area, if we add this all up, because we know our arc length now in terms of r, that's going to be 2rh plus 0.8 r squared. And then we're going to have 0.8 r. And that is our surface area. But it's asking us to show this, right? Well, actually, it's just in terms of r. So we really need to get rid of this h here, don't we? But we're also given the volume. How would we work out the volume? Well, it's again like that goes back to the argument of like it's kind of like a prism again. So you have this 2D shape, and then it's been extended or by a length, by a width or a length, right? So you have this cross section, this on the front of it. So here on the front, and then it has the same sort of cross section all the way through times by length. So the volume is going to be the area of the cross section, which is this sector here, times by h, right? How deep it is. So our volume is simply going to be the area of the sector times h. But the area of the sector h times the area of the sector. But we know the area of the sector, that's half r squared theta, which is 0.8. So that's going to be 0.4h r squared. And this has to be equal to 240, right? Well, therefore, hr squared, if you just simplify this a bit nicely, is divided by 0.4, which is 600, right? Well, okay, so what to do here? So we have two equations with r and h. Now, what do you do with simultaneous equations? You substitute one into the other. And actually, this is just in terms of r. So I need to get rid of the h in the surface area. How am I going to do that? I'm going to need to substitute h here. So that means h is going to be 600 over r squared. Therefore, surface area, if you substitute that back in now, in place of h, it's going to be 2r times 600 over r squared. And that's going to be 1200 over r. If you times h here by 2r, this times 2r gets us this. Okay. And then we have plus 0.8r squared plus 0.8r. Now, what does it say? 0.8 r squared plus this value here. Well, actually, it's quite interesting because that's saying that they should cancel out. Uh, We'll have a look at it in a minute. Yes, so it's the same answer, 0.8 r squared add r to 1680 over r. Okay, so that's a slightly different constant. No, there's no way I can bring the r into the fraction here, is there? You just get r on its own. I don't think so. Let's check our working again. So 0.8 r squared, we do have that over 1680 over r. Okay. So somehow this needs to go, and this needs to become 1640. Let's just check. So that's a rectangle piece. That's going to be r times h. R's the width here. This is going to be arc length r theta, which is going to be 0.8 r. That's going to be h. The volume again. Did I get the volume right? So that's going to be the area of the sector times h, the depth, I guess. Half r squared theta. Times h. Okay, that's equal to 240. Okay, check the other surface area. So that the rectangles RH with two lots of them. So that's going to be 2RH. And then there's two lots of the area at the top. Well, the area of the other sector is half r squared theta times up by 2. That'll just be r squared theta, right? So that's 0.8 r squared because theta is 0.8. Then have arc length. Oh, arc length times h. That's why I didn't include the h in it at the end. So arc length is r theta, but then I'm timed it by h. Okay, there we are. Okay, so I need to substitute h into there as well. Okay, so 0.8 r. I'm going to write that down here. There we are. Forgot I'm missing h there. 0.8 r, and then we're going to times it by the h, which is here, right? Use it here, so 600 over r squared, and the r will cancel. So you're left with 1200 over r plus 0.8 r squared, and this will simplify to what's 600 times 0.8? 480, and I think that gets us our number. 480 over r. Well, these we can collect like terms here. We can add these two fractions together to then get 480 plus 1200. You get 1680 over r plus 0.8 r squared. And is that not the formula for s, the surface area that they wanted us to get? It is cool. So we've got that right. Okay, that's probably the hardest part, right? It's realising the surface area bit, which is alright because I think this is like a GCSE. Well, yeah, all of this is really GCSE, really the first part. because you cover area of a sector and arc length in GCSE as well. Obviously not in radians, but yeah, and it's ironic because that's probably the hardest part of the question, in my opinion, because this bit's of differentiation. So we need to find the value of r for which s has a stationary point. So we're going to need to basically compute ds over dr, aren't we? Because that's and set that to 0 to be a stationary point. So stationary points, so that you should remember that's when ds over dr is 0. Well, we're going to have to find ds by dr, aren't we? But actually, before we do that, we need to make this an easier form to differentiate. So we need to bring this as a power, right? Instead of a fraction, which means we can differentiate it like a polynomial. So therefore, that's s. So therefore, ds by dr differentiate with respect to r. That's going to be minus 1680 r to the minus 2, right? So you times by the power and then you subtract by 1. And then plus 1.6r, right? 0.8 times 2, and then not 1 off the power. And then that's going to be minus 1680 over r squared plus 1.6r. Now that has to be equal to 0. Okay. I guess you could add the fractions, but really, if I just times by r squared, I'm then going to get minus 1680 plus 1.6r cubed is equal to 0 to get rid of the fraction here. If you're a bit afraid, I guess you could add the fractions. If you're a bit worried about, oh, I'm adding solutions of a time or something. But if you add the fraction, you get minus 1680. And then to get a common denominator, I need to times this top and bottom by r squared. So that'd be 1.6 r cubed over r cubed, r squared over r cubed, sorry. No, r cubed, 1.6 r cubed over r squared. Some times in the top and bottom here by, because this is over 1, isn't it, really, a fraction? Then I'll times it by r squared both sides. But then, if that's equal to 0, this numerator, sorry, has to be equal to 0. That's the same as here. So really, I'm just skipping at the steps by just timesing through by r squared. So you can play it safe if you want to, but essentially you just get to this. But then that means r cubed, or 1.6 r cubed, has to be 1680, right? And then r cubed divided by 1.6, you get 1680 over 1.6. So that'll be 1050. Therefore, r is just going to be the cube root of this, isn't it? Which is 10.16396 blah 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 centimeters. Okay. Well, that's the value of r, but how many? It doesn't say any decimal points. But actually, we can leave that as the exact value, can't we? We can just say r is the cube root of 10350, right? 1050. And then it says, prove by further differentiation that this value of r, and we probably got it right because we only get one value of r, which we've got here. If you're cube rooting, you do not do plus or minus. Because obviously when you say, for example, minus 1 cubed, that's still minus 1. We preserve the sign. So we only get one value of r there. But anyway, so then we need to find that it gives, in fact, the minimum surface area. So we need to show it's a minimum. This value of r to give the turning point. Okay, so that's 10.6 blah blah blah, or I guess 10.16 to 2dp. So, but then we need to prove that this is a minimum. How do we prove a turning point is a minimum? Or a turning point is a minimum. Well, d squared s by d r squared has to be less than 0 at r equals cube root of the value of r that gives the turning point, right? So a minimum has to be greater than 0, sorry. Okay. So obviously the minimum will look like this, by the way, obviously. So the minimum point here. So it's kind of like saying the curve's about to go up, right? So the tangent's about to go up. So the rate of change of that's gonna be positive, right? Anyway, so that's a condition for a minimum that has to be greater than 0. Well, then I just need to compute d squared s by, well, I need to compute the second derivative, don't I? Because I found the first derivative here, didn't I? So then I'm gonna bring that back again. So I'm gonna say ds by dr is minus 1680 r minus 3, was it, or minus 2? No, it would have been minus 2, wouldn't it? R to the minus 2 plus 1.6 r. So then I need to differentiate this again. And then deduce the minimum. So ds squared by dr squared. By the second derivative, again, we're going to times by the power. So it's going to be minus 2, lots of minus 1680 of r to the minus 3. So again, times by the power, knock one off, plus 1.6. So then that's going to be minus 2 times minus 1680. That's going to be 3360 r to the minus 3. Add 1.6. Okay, now I need to show that actually when I substitute this value of r in, that gives the turning point. It turns the second derivative to a positive, right? It's a positive result, which will then show it's indeed a minimum. So sub r is the cube root of 1050 into the second derivative. What do we get? So then d squared s over dr squared. I can use this fancy notation to show that this bar means I'm saying I'm substituting r is equal to this into this expression here. And then that'll be 3360 of the cube root of 1050 minus 3 plus 1.6. You don't have to rewrite it as a fraction and use the index, because we just care about substituting it in. We can use a calculator for that. So we don't need to do any like processing or anything like that. So I can just put that into the calculator. So 3360 of the cube root 1050 plus 1.6 of oh, hang on. Oh yeah, no, sorry, I'm waffling now. So the cube root of 1050 raised to the power minus 3 plus 1.6 will get you actually quite a nice number, surprisingly, 24 over 5. And actually, this is greater than 0. That means by what we said up here, this is indeed a minimum. So therefore, this is a minimum. Hence, our cube root of 50 centimeters, I guess, minimizes the surface area, right? And that should be your answer to that question. Okay. Hang on, it's equal to 5 apparently. Where have I gone wrong here? 1.6 and 3360 over r cubed, so yeah, that's all right. Did I get the value of r right? Yeah, it's 1050. Oh, it's because they rounded. That's why. No, it's because they rounded the cube root. So they put in 10.2 instead of oh, hang on. Hang on. I've got all the values right according to the mark scheme. I think they just rounded some. I need to check. Hang on. 1.6 and yeah, that expression's right. Okay. The value of r is right. So what did I substitute it in? R is the cube root of. What? How have they got 5? I got 24 over 5. But that's pretty damn close to 5. I think they just rounded it, I think. So, I don't know. I think they've rounded it to the nearest whole number. That should be right. I'm not sure how the mark scheme got 5. I don't know. Even when they're using their own numbers, which is my numbers, but they've rounded uh cube root of the cube root of 1050 to 10.2, and then they substitute 10.2, the rounded version, into here. And apparently they just, but I put that into calculator, and with their own number, you get 4.76. Uh, which isn't 5, so I'm not sure how they got. They must have rounded it up, I guess. I don't know. But that's the exact answer anyway. Uh, I know I'm not going to lose sleep over it unless if I see anything wrong here, I'll correct myself in the comments. But I think that should be right. Okay, we're on the final question now. Hang on, let me check the chat. Anything going on? Okay, I think we're good. By the way, if I should have said hello, but if I haven't, hello again. Okay, we're on the final question now. And we have this curve here, parametric curve. And really, the whole question boiling down to find the area of R and to split this up, which is quite nice of them. But it's a 9 marker. Oof. Okay. So the area is between x is 0 and x equals 4. Okay. So we need to integrate the curve between x0 and x is 4. So we need to show that the area of R is given by this integral here in terms of t. So our key method here is going to have to convert f into t's. Okay. But this is what I'm going to say, and I recommend this is the approach you should always take with parametric stuff. Is I'm going to first define this area in Cartesian, so in terms of x and y. But as I just said, the area is between x is 0 and x is 4. And that's going to be the curve. That's going to be y, isn't it? So y is f of x. Say, if we could find it in terms of x. That would be integrating y, the curve, obviously, with respect to x. Okay. Now, obviously, bear in mind y would be in terms of x because it is implicitly, I guess, a function of x, really. So we'd be integrating this whole function with respect to x. That's how you find the area of the curve here. And that's how it always work out. You put your bounds in terms of x, and then you put y dx. Hopefully you understand why. Think back to just, even in the early parts of the paper, think about how you integrate other functions. It's always the function of x or y, which is y equals f of x with respect to x between the limits, okay? So this is all in terms of x and y, I guess. Okay, so that is the area of R. We need to convert this integral then into this one, just in terms of t. So we need to convert everything into t. And that is going to be the step here. So I think the first bit is to look at the limits, first of all. So x is 0. That means 8 sine squared t has to be equal to 0. That means sine t has to be 0. So t then, wow, how do you solve? Well, t would be 0, right? Or if you arc sine it. But then obviously look at the graph of sine t, sine, that's 0 here, and then pi, and then 2 pi, and so on. But let's have a look. Well, t is only between 0 and pi over 2. So 0 is going to be our solution here. So that means t is 0. So that means when x is 0, t is 0. Well, when x is 4. So that means 8 sine squared t has to be equal to 4. Therefore, sine t, well, sine squared t is going to be 4 over 8, which is a half. So that means sine of t is going to be root of a half. So therefore, t, if you arc sine that, make sure to put it in radians now, because 2 questions ago it was in degrees. So make sure to put that to radians. So arc sine of root 1 over 2. Hopefully you get an exact number. Yes, you get pi over 4, which seems plausible, right? And that is in the interval here, because pi over 4 is less than pi over 2, okay? I know some people, oh well, 4 is bigger than 2, so perhaps it's outside the range. Think about it, divided by a bigger number, so this has to be smaller than pi over 2. Okay, so that's it in the range, so that's our solutions, right? Cool. So therefore, that's our limits. But now that we need to deal with this y. The y, we need to express, so we need to express every part of this in terms of t only. Well, we've expressed we converted the limits into t. Now let's deal with y. Well, y is already in terms of t. This is the definition. Y is 2 sine 2t. Plus 3 sine t. So that's quite easy. So then the last bit is to focus on this dx. The dx has to be dt. Okay, well, how are we going to get dx? Well, we're going to have to differentiate, aren't we? And we're going to get in terms of t, we're going to have to differentiate x with respect to t. Well, we know x is 8 sine squared t, right? I believe it is. So then I'm going to have to differentiate this with respect to t. So if I say alternatively, this is 8 lots of sine t all squared. Hopefully it's apparent that I can use the chain rule here. So dx is going to be 8 lots of, and then I'm going to times by the power 2. Then I'm going to times by inside the bracket, which is going to be cos t. And then it's going to be sine t. 2 the power minus 1. 2 minus 1 is just simply 1. So it's just sine t. Now we can evaluate this to say 16 sine t cos t. Cool. So that means therefore we need dx. So we just times across. So you're going to have 16 sine t cos t dt. But actually everything now is in terms of t. So we can rewrite this top integral in terms of t by substituting everything we have. Because we essentially converted everything from the x world into the t world, which is what we want. So therefore the area is going to be between, well, when x is 0, t is 0, right? So say t is 0 and t was pi over 4, if you remember the limits here, between y, which was 2 sine t, 2 sine 2t plus 3 sine t. And that's between, and then dx, which is 16 sine t cos t dt. Okay, so that's all in terms of t now, but we need to get this integral here. So I think what I'm going to say first is what I'm gonna do first is factor out the 16 and see what we can get. So it's gonna be 16 between t. Well, I'm gonna just say pi over 4 now. No need to put the t equals 0 between and I'm gonna say sine of t cos t of 2 sine 2t plus 3 sine t. Okay, now let's compare. I kind of know what to do next, but let's compare. I do not have a cos of 40 here, which is quite interesting. So we're going to need to use double angle, clearly, right? Okay. But talking of double angle, I notice this is a double angle. I think this might help. Because with integration, remember, it's always helpful to use double angle to reduce it down. Because we cannot integrate high powers like sine squared t, but we can integrate linear angles. Okay, so that's why we use double angle to reduce our powers down. But anyway, so sine t cos t, you should remember sine of the double angle sine 2t is 2 cos t sine t. Therefore, the area of the integral is going to be 16 lots of pi over 4 and 0. But sine t cos t is going to be half sine 2t. And that's going to be between 2 sine 2t plus 3 sine t dt. Okay, then I'm going to bring that half out. So I'm going to say that's equal to 8 between pi over 4 and 0. And then I'm going to expand this out because I'm not too sure what I can do next. So sine 2t times 2 sine 2t is going to be 2 sine squared 2t plus 3 sine t sine 2t dt. Okay, so what can I do now? Well, again, I noted. Okay, well we have an 8. We have a cos 40 here again. We have it all in sine, and I need a 4t, and I need a cos t with this. Okay, well, what can I work with now? Well, there's. I think, like I said, we don't want any higher powers of sine squared, do we really? But I think we can use double angle on this, can't we? If we then recall that cos of 2t is cos squared, well, 2 theta, I should say, is cos squared theta minus sine squared theta. Because it doesn't matter what the angle is, right? Any angle. But we have a sine squared here, and we have a cos 2 theta here. But actually, we can further rewrite this using the Pythagorean identity. Cos squared plus sine squared is equal to 1. This is going to be the same as 1 minus 2 sine squared theta by replacing cos squared from here. So cos squared is 1 minus sine squared minus another sine squared. Therefore, we can say 2 sine squared theta is going to be 1 minus cos 2 theta by rearranging. Yeah, but notice these are now matching. 2 sine squared 2t, 2 sine squared theta. If we just say theta is 2t, therefore 2 sine squared 2t is going to be 1 minus cos 2 theta, which is 2 times 2t, which should be 4t. And that's where we get our 40 from. So therefore the area is going to be between pi over 4 and 0 by substituting this in. Of what 8 lots of, sorry, between, well, it's going to be 1 minus cos 40. And we still have this bit on the end, don't we? We have 3 sine t sine 2t. Okay, let's compare with answer. Okay, so we have a constant minus cos 40, but we have this expression here, sine squared t cos t. But notice these are not in double angles. These are single angles just in terms of t. What we've got here is, if we look here, well, the first bit matches, but here we have a 2t here, and we need a sine squared and a cos. I think we can use the double angle here to say, well, sine 2t is simply 2 sine t cos t. If we remember the double angle for sine 2t here, which we did here, remember? Hopefully you should remember that. And I think if we expand this out, what do we get? So that's going to be between 8 of pi over 4 0 of 1 minus cos 4t plus 6 sine squared t cos t, right? Sine t times cos t, sine squared cos t times 6. Now, is that the answer? Almost, but we need, it's in the same form, just the numbers are different. But there's no number in the front, so we need to bring the 8 inside. I know it says 8 here, so I think if we times by 8 inside the integral, we get the answer. So then that's simply then pi over 4 and 0 of 8, if we bring the 8 in now, plus 6 times 8, which is 48, which is the number they wanted. And that is your answer to part A. That's the integral they wanted. Cool. And then part B, I presume it's to evaluate the integral, I assume. But let's just double check. Hence using integration, find the R. Yeah, so you need to integrate the final integral. So you just need to integrate this. Okay, I'm going to need more space here. Let me create another document. Okay. Hopefully that's clear now. So I'm going to rewrite our integral. So obviously we have the integral of 8, what is it? 8 minus 8 cos 40 plus 48 sine squared t between pi over 4 and 0 cos t dt. Was that it? Let me double check. Yeah, cool. So then we need to evaluate this, but actually, this is, if you split this up, the integral of pi over 4 and 0 of 8 minus. So I can say, I want to bring the 8 out again, actually. 8 lots of 1 dt minus 8 lots of cos 40 plus 48 lots of between pi over 4 and 0 sine squared t cos t dt. So that's 4 cos 40 dt, and then add to 48. Cool. So we can split the integral up to make it nicer for us, and I can factor the factors out to make it easier to see what I'm doing. Wow, this first bit is quite nice. So that's going to be 8 between, well, 1 will integrate to t, wasn't it? Between pi over 4 and 0 minus 8 lots of cos 40. Well, that's going to integrate to a quarter sine 40 between pi over 4 and 0. Because notice you do not do a minus here because we are integrating. Differentiating cos gets minus sign, but we're doing the opposite. So integral cos would just be positive sign. And because we've got the 4 here, differentiating it would be minus 4 sine 40. We times by the factor, right? But here, because we're integrating, we divide by the 4. Okay. And then we have this bit here, 48. Okay, well, this isn't immediately obvious to see, actually. But I think, doesn't this look vaguely like the reverse chain rule now? We have, and the chain rule goes like this, if I remember correctly. It's f of u times by u dash in the integrand. Well, we can say this is the same. This part in the integral is the same as sine t squared times by cos t. But isn't this this is the reverse chain rule? Okay. Well, we have a function here that sine t being squared. That's like x squared, I guess. I guess. Well, we're inputting the composite function sine t, squaring it, times by the derivative, which is cos. This is actually the reverse chain rule. And I think that's by far the nicest way to integrate this. It's going to be a whole mess if you try and perhaps use by parts of substitution. You have to be quite, I think you have to be quite imaginative with your substitution, although it can be done. But I think the reverse chain rule is probably the best to see this. So then what does that mean? Well, if it's in this form here, we then just need to consider the next power up. So let's consider y is and not the same y as in part A, but just a generic y, which is sine cube t. And I recognise, well, actually, y dash or dy dx. Well, that's going to be, if we use the chain rule here, because that's sine t cubed, that's going to be 3 times what the derivative inside, which is cos t. And that's then going to be sine t, and then 3 minus 1, knock off the power by 1, you get squared. So that's 3 sine squared t cos t. Why is that just not the exact number we have, but with a 3 on top? But we can adjust for the scale factor by dividing by 3 and then differentiating, because obviously the multiple in differentiation, you can just factor that out. So then it'd be times by a third at the end. 3 times a third would just get a sine squared t cos t, which is exactly the integral. So that means if we are differentiating y to get to this, then that means the integral of this in reverse would just be this function here. So that means the 48 lots of the integral is just going to be a third sine cubed t between pi over 4 and 0 via the reverse chain rule. And hopefully you can spot that. It's very tricky integral, that is, for normal maths anyway. I'm going to get rid of this now, but that's essentially the reasoning behind it. If you have a function of this form, that's a reverse chain rule. So it's, but yeah. And I guess you could notice it as well, because, I don't know, you're kind of splitting this into power 2, and then you have the derivative of sine. So you can then get a function like this. Anyway, so that's kind of the idea behind that. So then I'm going to evaluate all this. So 8 lots of, well, t between pi over 4 and 0, that's going to be pi over 4 minus 0, which obviously goes to pi over 4, minus 8 lots of, and then that's going to be a fourth sine of about 4t, 4 times pi over 4, that's going to be pi, right? And then I'm going to say minus a quarter sine of 0, right? And then I'm going to say plus 48, and then evaluate the third definite integral of a third sine cubed of t. That's going to be pi over 4 minus a third sine cubed of 0. And then we just bung all that into the calculator. And so that's going to be a 2 pi, right? And then minus 8 lots of a quarter sine of pi minus a quarter sine of 0. That will get you 0. And then this last bit here, 48. Apparently you get 4 root 2 for the last bit. Is that? Let me check that. Yeah, the third sine of pi over 4 all cubed. Yeah, minus a third of, well, sine of 0 just go to 0, right? Yeah. Okay, I assume that's right. But then our answer is going to be 2 pi plus 4 root 2. Okay. Does it ask to give an exact form? Uh, Right, exact form, but any particular form. So I guess the ans is 2 pi plus 4 root 2 by the workings we did there. No, it just says find the exact area. Okay, so I'm presuming that's the answer. Let me just check the mark scheme. Okay. Yes, you get 2 pi before root 2. Cool. And that's the final question. Um, yeah, and so that's the end of that paper then. It went a lot more nicer today. I didn't really make any mistakes. Uh, which is funny because it's the harder part at the end of the paper. But yeah, I don't know, man. But anyway, I'm not going to jinx it now. That's the end of that. So, I guess for this, again, the part A, just write the integral, and this is for any parametric question. Write the integral in terms of x or y, whatever, how you'd normally express the integral, and then just convert everything into t's. So you express x is 4, use the equation to get t, and then substitute y in for t, and then differentiate to get dx. Then you do some trig substitution, and then you get this answer. Use your double angles, right? Uh, Double angles is very common with trig integration, right? Because they generally knock down powers of higher powers, right? So then you get a single power with a double angle, which you can integrate. Um, And then for part B, I guess the hardest part is noticing this integral here. The first two should be fairly straightforward. You should hopefully spot its reverse chain rule. I think there are probably multiple ways of doing it. I see what the mark scheme does. Perhaps, like I said, you could convert this into some sort of double angle, perhaps. Uh, um, I'm not sure though. Uh, I don't know. Well, I know sine squared you could write in terms of cos 2t. But then that's times in by cos t, right? So then you have cos squared. No, it won't be squared because they're different angles. Uh, but then I guess you could say that cos 2t, so sine squared, times that. Well, it's more specifically, what was it? Sine, what was it? 2 sine squared t was, what was it? 1 minus cos 2t? Was that the answer? I can't remember. Uh, yeah, 1 minus cos 2 theta. Um, so then therefore, any multiple of sine squared, we don't care about the multiple. So then you're saying 1 minus cos 2t of cos t, that's cos t, which you can integrate, minus cos 2t cos t. I guess then you could say that's cos squared t minus sine squared. Well, how would that help? Because then that would go to cos t. Obviously, we don't care about that. We can integrate that. Then that would be cos cubed t minus cos t sine squared t. But we want to get rid of the higher powers. I don't think you could do it without some sort of clever substitution or the reverse chain rule. I'm not sure. I might check the mark scheme. Maybe they do alternative methods. I'll be interested to see the other methods to tackle this because the one that spots to me is reverse chain rule. But is there a way you can do it with double angle? I wonder. I know there's a further maths method. There's a way you can use complex numbers to express cos cubed t in terms of like cos theta and 3 theta. But without that, is there another way? Hmm, not sure. I don't know. I'm going to leave it there then. I'm not. I want to extend the live stream. Let me check the mark scheme just before we leave. Is there any methods they come up with? Well, the mark scheme just literally integrates it without showing any method. I think, yeah, substitution, you could say u is sine t, which makes sense because sine t is what we're using for the reverse chain rule, because we say sine cube t. Uh, so that you could use substitution in that sense. Yeah, no, the mark scheme doesn't really say anything. It just says students may use other methods other than the reverse chain rule. Don't know. You know what? That's a question I'm going to leave to other people. Is there any method apart from substitution to say via chain by part? Well, by parts maybe. I think by parts. I think I can spot how to do that as well. It's just a bit tedious, it's a bit harder than normal. But anyway, I'm going to leave that there. But yeah, that's the end of the paper. And yeah, so bear in mind also I did part one to this. Like yesterday, last stream. Make sure to check that out as well. Um, but yeah, that's June 2022. And yeah, so as for for paper one, um, for revision, because obviously it's on Wednesday, right? I think so. Obviously, GC Maths has their exams on the same day on Wednesday for their paper too. So I'm a bit like I want to cover both, but I'm planning the GCC to do Saturday, Sunday. So then I'll probably do another revision stream on Monday for A level, and then probably Tuesday as well. Tuesday I'll probably split half A level, half GCC. But I don't know what to do. Should I do another past paper? Because I think I have time for one more past paper, and that'll probably be paper two for this June 2022. But I don't know if I want to do a past paper or compile questions. But the difficulty with that is there's nothing you can predict really for um, paper one because obviously it's the first paper, right? Anything could come up really. But I do notice the same sort of questions come up every year. For example, there's always going to be a what's it called? Uh, oh, First principles question. There's going to be a trig proof and solving question like we just did earlier. There's going to be an exponential modeling question, or perhaps logarithmic, but usually exponential modeling. I'm noticing quadratic modeling is coming up as well, so that's where you have to form a quadratic based from certain conditions and data they give you. So you have to form a quadratic function. What else is there? Let's just have a look through this paper, really. What else did they come up with? factor theorem, I guess. Although not always it comes up, but to be fair, it should be fairly straightforward if that does come up. Proof, I guess, but there's loads of different proofs that can come up, really. A circly type question, uh, something like this, where you have to find the centre and the radius, and then you have to intercept with a tangent, and then use a discriminant, that sort of thing. But this is int that doesn't really come up, to be fair. Yeah, a modelling question, some sort of graph work, proof, uh, like some sort of like differentiation, returning points, stuff like that. Iteration doesn't really come up, apart from like one question maybe. Vectors, although there's many vector questions they can ask really. They can either actually just like to find like they can either give you a geometric problem like the rhombus, or they will just simply ask you to find like AB given position vectors A and B, which is simply OB minus OA. Then they actually find the length. You know, the vectors will come up, but yeah, we can't really predict what type of question. You just have to be prepared. Like exponential modelling here, like I just said, that's very common. Um, again, graphs. Integration comes up usually. Just actually to compute an integral somewhere. Series comes up as well. Like I said, this trig sort of question. Part A, you have an identity, and then part B, you have to solve it using the identity. And also, I've noticed the final question for paper one tends to be a really difficult or lengthy differentiation or integration question. I've noticed that 2023 was an awful differentiation one. It was something like e to the 3x, x e to the 3x over like, I don't even remember now, over like x squared, or I can't remember what it was. Basically, it's a quotient rule, but you have to use product and chain rules as well. But obviously, and then this year it was a really nasty. The year before was a nasty integration question. So for the final question for paper one, I would expect to really brush up on your calculus and your integration differentiation. So I'm going to say a hard diff or integral question, and also expect a simple integration question or simpler integration question. So where you just apply by parts or make a simple substitution, or integrate using another method, right? So those are the sort of topics I'd expect. So first principles, trig proof and solving, exponential modelling, quadratic modelling, integral question, differentiation question probably, and a harder differentiated integral question as well at the back of the paper, and probably like a proof question. I don't know. But those are the sort of topics, but they come up every year. But basically, I think past paper is probably the best way to practice. I think. Because then I can tackle basically every, and also like a binomial expansion question. Those topics come up. The same sort of questions come up. But anyway, I think what I might do is just do paper two for this next time, perhaps. Um, 'Cause, in paper two, then we can start to rule off topics and do predicted stuff and do questions that are very likely to come up based on what we know on paper one and trends from past papers. But when it's the first paper, it's very, very tricky. It really is. So you just got to learn everything, and that's why I think doing past papers and me going over some will help, because we get direct practice, right? And we practice all the topics. Anyway, I'm going to leave that there, and then we'll stop waffling. I'm going to put this on YouTube. So yeah, that's June 2022, paper one. But I am going to leave it there now.